Hello and welcome to my presentation on a robot that I worked on during the summer. I'm going to be talking about what we did and how we achieved the end results. So, our project name is Shaky Steve, and it was named after a robotic assistant. Well, it was a sort of an educational robot that was designed in Columbia lab before I came in. And before we get too much into the project, I want to talk a little bit about myself. So my name is Ege, and I'm from Turkey. I'm currently a high school senior, and I'm applying to colleges. And I'm doing this to gain some experience in the field of research, especially when it comes to robotics and doing firsthand work in the lab. And I have prior experience in mechanics and robotics. Also, I'm fairly proficient in programming in general. So the motivation of the project stems from if we can use NLP to control a mechanical robot. And this has actually been experimented on by different companies, the most notable being Apple. Apple themselves have worked on an LLM-powered hardware architecture. But essentially, ours is just an experiment to see if specifically ChatGPT can control moving robots. And we use Python for the code generation because that is the most versatile language for AI at the moment. So this is Steve on the right, as you might see. It's a little robot. And it's educational, meaning that it can't complete high level functions, and it's mostly used to teach people how basic movements and work and how the software operates on a basic system. The philosophy is that it has an open hardware and an open software, meaning you can tamper with it in any way you want. And it has been incrementally built over many summers, meaning that I am not the only person who has upgraded Steve. I'm far from it. I'm just the last person who's done this. And we've also recently updated the Raspberry Pi processor for better computing speed and general an increase in intelligence and how it um, can understand commands. So I want to give a little demonstration about what the old Steve looked like, and we have a little video here. So as you can see in the video, the servos were functional back then, but it uses the old Raspberry Pi 2B, meaning that its computational capabilities were limited by the hardware compared to what we have now. It was controlled by a 3D mouse primarily, and it didn't take voice commands very well. It had shaky servo movement, and most importantly, the software wasn't there yet. And Google Assistant was actually used before we integrated ChatGPT, but Google Assistant was not a very effective way to make it take commands, and I'll talk more about that later. But for now, I'll move on. So this is what the old voice control looks like, and I'll play a little demo of it. Say hi, Steve.
Hello there. So good to talk to you. I've been pondering over something. Maybe you can help. What do you say?
Of course.
Great. Here's an important question. Is it okay to have pizza for breakfast?
Sure, why not?
Looks
Yeah.
like you are busy. I'll be here if you.
So as you can see, it had a very slow response time. It was unpredictable and generally difficult to work with. And this was when we were using Google Assistant to, interact with Steve. And the limitations of the previous design, well, primarily was due to a slowness and a lack of computational skill, but some other points of interest included that commands like high five were hard coded and others could not be experimented upon. For example, I could not say, Steve, turn left 180 degrees. Like the machine could not make sense of what I just said. It only understood like default commands like wake up, sleep. And it did not have silence detection, meaning it didn't understand when to stop listening to you, when to start listening to you. And this was also due to the Stct engine being inconsistent because we did not use Google's API before that. We used a different approach, and that was not very accurate. Here's a basic map of what Steve's hardware looks like, and it has multiple components, as you can see. But most importantly, Steve uses Wi-Fi to communicate with the endpoint. So when you make requests to ChatGPT, Wi-Fi is how it's being transferred. And we have the 3D mouse, which is connected via the USB port, and the Raspberry Pi itself connects to the servos, the PWM bonnet, the jumbo LEDs for silence detection, and it's basically it basically provides ease of use because the jumbo LEDs make us see when the microphone is active and when it's not. And we also have the voice bonnet and the audio speaker / mic. So essentially, it has components that take input, output, a brain, and it can send it over signals. And here's a little more detailed version of the software architecture. So we have a lot of different files, but primarily it starts from the input, right? So we detect sound as the input. So we can, as you can see, there's something called ALSA, which means Advanced Linux Sound Architecture. So we use that library to get the voice, and then after we transcribe it into text using the Stct client, we send it to ChatGPT, and ChatGPT generates the Python code, which can then be run by the main program. And the main program maps to two different parts essentially, but the one that actually controls the robot is called RoboArm controller, which includes all the servo functionalities. And there's also the LED controller, but this was for the Stct implementation. So the LEDs would blink accordingly, when they would blink differently when you were speaking versus when the microphone was inactive. And we have the mouse component, but it's separate from the Stct. That's directly connected to the servos, meaning there's nothing in between. So you can just control Steve using the mouse as well. And we're using Raspberry Pi OS, meaning it's a Linux-based architecture. And you can see what type of peripherals we have. So this is what we achieved at the end of by the end of the project. So this is what the structure looked like. So the project outline was essentially we wanted to replace Google Assistant with Google Stct Cloud Service for voice recognition. We thought this would be better for longer text, and it would suit Steve better for natural human languages, because sometimes what default speech to text engines do is they cut the input too much and it sounds unnatural. And we wanted to use ChatGPT for more flexible control, meaning we didn't want to just say stuff like high five, sleep, wake up, and instead wanted Steve to extrapolate and read in between the lines. For example, I could say point down, move left, and then slowly turn your base towards the right again, and it would understand what I said and turn it into Pythonic code. And this is more about the implementation, but to store the functions, we had a little JSON dictionary we used to store the calls and the different functions in that the user provided. So these functions could also be called for later usage, and they were not lost if the user forgot them. So there's also one more point that has been crossed over, it's called integrate Google text-to-speech for voice generation. We decided to focus on the other aspects of the project because we deemed them more important, and the Google TTS was trivial at the time. So these three were primarily the main objectives. So the Google Sct integration was as follows. We first get the module gets the speech and translates it to text, but the way it does it is it has like a live recorder, so the input from mic, and the output is as text, so the user can also see what they're saying and how they can interact. And this was done for to make users to basically provide ease of readability. And we have two different commands, so microphone activation and microphone deactivation, and these are controlled by the button on the 3D mouse, meaning one click of one of the side buttons activated the microphone, and either automatic silence detection or just a manual click on the button again deactivated the microphone and closed the input. And it uses the Google Sct engine in the cloud, so it was primarily Google's Sct engine that was relied when transcribing all the text. And this is a high-level overview of what the machine does. So we have the 3D button, mouse button click, which activates all of so it serves as a catalyst for all that happens after. And that triggers the activate microphone response. This listens to the speech, and the client is it goes between Steve and ChatGPT. So we use the voice transcription to get what the user said, and then we use ChatGPT to get the code and then send it back to Steve. This was the prompt we used when training Steve. It was essentially experimented upon and to see what keywords would work best to train Steve. But this is like a basic overview, so we gave context for it. So the blue sentence is just like some general context. So we defined the predefined functions that were in the RoboArm files. And we also added some additional notes like do not define the functions. And when the user specifically says execute the corresponding Python function. We also didn't want it to add the Python tick mark signature at the beginning of every code snippet. So we devised a little algorithm to get rid of that, even if it did. So I'm going to go over the demo, and here's what it's going to look like. So there are some basic commands, as you can see, and there are some advanced commands. Then there's the 3D mouse control part, and then we're going to try to program the robot using ChatGPT with advanced functions such as time.sleep, and we're going to try calling them, the functions. So the first function we're going to call is Steve wake up. Wake up. And the terminal basically gave us the command, which was reset. So the terminal printed what the ChatGPT sent us. So ChatGPT set Steve to its default position by calling waking up. And here are the predefined functions that ChatGPT is allowed to use when giving us the code snippets. So it primarily relies on these for when it gives us something new, or like when it's trying to create like a mash between what it had before. So for example, I could combine commands torso and shoulder. They don't have to be separate. So Steve, close clamp. And the terminal shows that clamp 0 was called, meaning that Steve accurately predicted that the 0 value for the clamp meant that it would be closed. I also want to pay notice to something very important. So when we were defining the functions, we also gave it endpoints. So for example, you can see that function clamp closes 0 or opens 0.03, the robot's clamp. So by defining the edges, it makes ChatGPT's job easier when creating code snippets, especially when you're giving it boundary conditions. So here's a more advanced command. Steve, rotate wrist left, wait for 1 second, and then rotate wrist right. So we get 3 commands this time. We get wrist LR -90, which is 1 edge. We get time sleep, which is important for making it wait, or it's the user delay. And we finally call the right command, which is rist LR and then 90. And here's one that actively uses time.sleep and a for loop. So for example, we're gonna try calling it with the following prompt. Steve, using time.sleep, slowly move your elbow up. So so ChatGPT not only generates the code necessary, it also imports the library necessary, which is important. So we have time and we have a simple for loop that basically makes the robot wait for every iteration of the loop, which achieves the desired slow movement. So we can also control the movement speed using ChatGPT, which is something that normally you wouldn't be able to do with just the 3D mouse. So you're actually adding to how freely you can control the robot. Steve, using time.sleep, slowly rotate your base left. And this time for the output, we see that the time library is not important to get imported again because we've already done that before. So in a for loop, we have the same logic. We move it by angle degrees, and it's time sleep 01, meaning that it would slowly move it once again. And finally, this is going to be the most complicated function we've defined up until now. So Steve, define a function called alpha. The function executes the following sequence slowly. Reset to default position, close clamp, move the elbow up, move the base left, move the base right, and then finally sleep. Steve, define a function called alpha. The function executes the following sequence slowly. Reset to default position, close clamp, move the elbow up, move the base left, move the base right, and then finally sleep. And we actually get a very neat code structure here. So we have the function definition, and then it repeatedly follows all of the commands. So it calls reset because it needs to reset to the default position, and then it waits. So it closes clamp, moves the elbow up, moves the base left, moves the base right, and then finally sleeps. So this code is basically generated by ChatGPT in the context of what the user gave them. If the user is more specific, the output will also be more detailed and it will probably work better. But this is like for a general command, this works very accurately. Steve, alpha. And before we take it any further, I want to talk a little bit about how this can be improved. So first of all, Steve was trained on a very simple prompt, and I believe that using NLP experts, we could engineer the prompt to give ChatGPT more details about Steve's structure, which could make it understand the movements better. Because essentially, what ChatGPT currently sees are just points of interest. It just sees unrelated vectors in an arbitrary space. But if we somehow train ChatGPT on Steve's model, then the actions would be much more accurate, and Steve would actually have awareness of a 3D space. So this is primarily how the code can be expanded, especially from an NLP perspective. And also, I believe a website serving as a basic documentation for Steve, like a demo, how it works, how it can be upgraded, and basic open source documentation would serve to be beneficial for anyone interested in robotics. So here's a general summary. What worked was the Google's cloud speech to text model, the GPT-4o model, which was trained extensively on data because we used the prompt. We made it so that the simple commands work. Essentially, you can stack commands on top of each other and it won't get confused. However, for more complex commands like assume the shape of a swan, it would need more spatial awareness and it would not always perform what we want. And it currently stores the functions in memory, meaning that it doesn't get deleted after it's run. So this is a useful thing if you want to keep calling the functions over and over again. So this was essentially my project that I worked over the summer, and thank you for listening to me.
Steve, high five. Steve, sleep.